Hi, my name is Gracie, and this is my fourth presentation for a physics lab. The purpose of the lab is comparing the difference between an analyzed video of an oscillating mass on a spring compared to the computational model given the same initial conditions. To do this, we're taking a video given to us and we're tracking the position frame by frame in the tracker app, and using that resulting data, we're comparing it to the computational model that we adjusted for our initial conditions given to us by the lab instructors. Here are some of the fundamental concepts. These become very important in the coding process because we use these equations to solve for a lot of the variables in the code, which I'll show you. But spring force, oscillation, aspects of the energy principle, and then some kinetics derived from Newton's second law are going to be the models and principles used in the computational model. And it's also explaining the movement we observe in the real video. The system is the earth, spring, and the mass, and there are no surroundings. We're using the internal energy principle, as you can see here, since everything is in the system, and so that would make the surroundings not applicable. And the initial conditions are that the mass is hanging on a spring at rest, and of course the objective is comparing the computational model to the model we got from the tracker application. A brief overview: they do follow the same pattern very closely, but there is some slight variation between the tracker app and the in terms of the position versus time graphs between the tracker app and the computational model. And here is the change in energy versus time. So using tracker, I used the auto tracker, but I did watch it frame by frame to make sure that the auto tracker was following the mass on the spring. And as you can see, the X and Y positions are oscillating back and forth throughout the video. And the computational model, as I said before, we use some of those fundamental principles to solve for example, F spring, F net, F grav, and we use these forces to update the velocity and position every frame to give us a good data set to compare to the tracker app results. And solving for K, delta UG, E being a total energy change, these are all part of the fundamental principles I mentioned before. And going more into the results, the comparative model showed strong similarity with only slight variations between the position versus time graphs. And the change in energy versus time, the oscillations do a really good job at canceling each other out in terms of delta U grav and delta U spring. And as you can see, delta K oscillates along with the peaks of them. And so all of these are going to sum up to delta E, which is 0. Possible sources of differences. The computational model does not take into account other smaller aspects of movement such as drag, and a possible source of error is, I'm not exactly sure if I calibrated the original video perfectly, which would result in variation between the computational model and the tracker application model. Yes, the energy principle is satisfied. As you can see from this graph here, all of these energies, especially you can see it well with delta U grav and spring, they do a good job at canceling each other out. And delta E being 0 means that the total energy of the system is unchanging throughout the oscillations. And the period of oscillation for X, this was estimated just from the tracker data. I estimated that the period of oscillation for X was 1.425 seconds, and for Y oscillation is 1.5. They are very close, but they're not exactly the same, which could explain the slight variation between the two. As you can see, they don't perfectly line up, but they are quite similar from the tracker data.